This video will cover regularization. By the end of this video, you should understand what are regularization methods, how can regularization methods address overfitting, what are the advantages and disadvantages of regularization versus cross-validation for feature selection. Regularization methods are designed to address the overfitting problem. Remember that overfitting is a common problem in model selection, and overfitting is a problem where we have this tendency to choose models that rely on irrelevant features. Overfit models can perform quite well on training data, but then make poor predictions out of sample. Overfitting, or what is often called the feature selection problem, is a big challenge in data science. Modern datasets may have hundreds or thousands of possible features, but only a small portion of them are relevant, and those are the only features that we'd like to include in our models. So far, we've dealt with the overfitting problem using cross-validation. Cross-validation works because models that rely on irrelevant features will tend to make poor predictions out of sample, and so they'll tend to have relatively large values of the loss function when evaluated out of sample. But are there other ways we could protect against overfitting? Again, overfitting is a problem because we're including irrelevant features in our models. And this is because the modeling tools that we've used so far are greedy. Adding features, even irrelevant ones, increase the model degrees of freedom, and so they always reduce the value of the in-sample loss function. So how do we prevent a model from being greedy? Well, how do we prevent people from being greedy? One way to prevent models from being greedy is to give them a budget for features. For example, no matter how many candidate features you have, you allow the model to only include 2 of them. You're going to choose the best model using at most 2 features. This is a way to prevent overfitting because you're going to limit the number of features that are included in a model. But what problems might you see with this approach? The proposal I've given you here gives the model a budget of 2 features, and so that reduces the chance that we'll include irrelevant features since there's only 2 to choose from. But what if more than 2 features are relevant? We might wind up excluding relevant features. Could you think of a better way? In the end, we want models that are balancing against 2 factors. We want to make sure we include all relevant features. These are good for predictions. But we also want to balance that against the chance that we include irrelevant features, which are bad for predictions because our models will perform well out of sample. What would an economist do in this case? They'd weigh the benefit of adding a feature to a model against the cost of adding a feature to a model. So what's the benefit of adding a feature to a model? If the feature is relevant, our model should make better predictions. But what's the cost of adding a feature to a model? If the feature is irrelevant, the model will probably be overfit and it will generate worse predictions out of sample. An economist would balance the benefits, getting an improved prediction from your model, against the costs, the risk of overfitting, whenever adding features to a model. They'd add features until the costs equal the benefits. This sounds really complicated. How would we make it work? The easiest way would be to make it expensive to add features to our model. How could we make it expensive to add features to a model? We're going to do this through a process called regularization. Regularization is an approach to prevent overfitting. It adds a penalty for complex models to the loss function. Models with many features get a larger penalty. This balances the trade-off that I described earlier. Adding a feature improves model fit or reduces the value of the loss function, but adding a feature also increases the complexity of the model and increases the penalty in the loss function. This means you can balance the benefits of improved fit against the costs, which are the potential for overfitting, embodied in this penalty. So I've said regularization involves a penalty. What does this look like? It's part of the loss function. Remember, the loss function expresses your preferences over different types of prediction errors. The penalty is going to express your preferences over model complexity. More complex models will increase the value of the loss function more. So what exactly does this regularization penalty look like? It depends on your preferences. The penalty might penalize models with many features, penalize models with features that don't have much influence on the predictions, or there could be many other ways you construct this penalty. Regularization is useful for feature selection. It's going to help us decide between relevant and irrelevant features in our models. But we've already learned cross-validation. Why do we need something else? We started with cross-validation because it has a lot of advantages. In particular, cross-validation simulates the process of evaluating model fit out of sample. This is the gold standard for model evaluation, and so cross-validation is conceptually very appealing. Cross-validation also gives us a guess of what the value of the loss function will be out of sample, since we're always evaluating our models out of sample. It also allows comparisons across all possible models, regardless of the particular modeling tool used. As long as you can calculate your loss function, you can perform cross-validation. Regularization has some important advantages too. Cross-validation requires training and testing each candidate model many times. In contrast, regularized modeling tools usually only need to be run once to select relevant features on the first try. It's often many orders of magnitude slower to use cross-validation as opposed to regularized modeling tools. So if time is an important concern, you might prefer regularization over cross-validation. Another advantage of regularization is that it uses all of your data all at once. Cross-validation requires dividing your data into training and test sets. Properly dividing your data can be complicated. For example, if you have data that come in a time series, where underlying factors may have changed over time. And even if you do it correctly, some of your cross-validation folds might contain weird data that give you spurious results. Regularized models use all of your data. This means you don't have to worry about complications with the way you divide your data, but it can also be an advantage when you don't have many observations to work with. In the real world, cross-validation and regularization are complements, not substitutes for each other. We'll often use regularized models to do a first pass at feature selection. This allows us to quickly eliminate irrelevant features, but then we'll do more fine-tuning using cross-validation. We might iterate through this process several times, of first using regularization, then using cross-validation.